おはようございます。J さんクーと申しますけど、日本語が下手でから、それから英語で話します。Okay, so today I'm going to be talking about some software and an algorithm I've been working on to compute folded states of origami. We're talking about actual folded paper now, not engineering anymore. So should be a fun new direction for this session. Okay, so really the goal that I think about with computing folded states is I want to be able to, as an origami artist, I want to fold paper, but I also want to be able to fold paper digitally because that can be faster. Maybe I don't have a sheet of paper and maybe I can document my my journey via diagrams online rather than having to do it with my hands. Maybe I don't have thin enough paper, or maybe my ability is not so good, and so I'd like to be able to simulate that online or on a computer. And there's a lot of simulations software available. Here's a good one that's for three-dimensional modeling that came out of one of Eric Demaine's classes that Mitani-san was talking about earlier. But the difficulty here with this folding simulator, it's great for getting three-dimensional shapes, but it doesn't do anything about layer collision or collision detection between faces of the model. And so what you see is in the rendering, these things can take shapes that you would not be able to do with physical paper. On the other side, you can also have some simulators online. For example, this simple folding simulator by Robbie Kraft within Rabbit Ear, his JavaScript folding library, which is able to do a limited set of flat folding operations, namely simple, infinite all layers folds. People who know that literature will know what those things mean. Basically, you overlay an infinite line on your folded state, and you take all the layers on one side of that line and fold it on top of everything on the other. And that's a simple infinite all layer folded state. And that's very nice, in fact, to simulate because you're always able to ensure that the folded state has a stacking order, an acyclic stacking order, where you can actually order the faces from top to bottom on this model. So it's actually computationally very easy to simulate. But unfortunately for general origami models, such a linear ordering of the faces is not always possible. In particular, this very simple pinwheel model that's traditional, and many people know how to fold this model. If you were to fold up this crease pattern, of course, it has a folded state, but that unique folded state is cyclic. There's no top face possible on this model, and so I cannot linearize it. So that makes it, the question then remains, how do we represent such a model if I can't tell you an ordering of the faces? How do I communicate to someone else the exact folded state that I'm interested in? Here I'm calling the left picture a crease pattern, the right picture a folded state of that crease pattern. And single crease patterns can admit multiple folded states, okay? So we need some kind of representation of a folded state that is more than just the crease pattern, right? The crease pattern does not uniquely identify a folded state. So we need the crease pattern, the location of the creases on the page, as well as a valid layer order of those faces when they overlap. So essentially the crease pattern says where all of the creases will be on the paper and how it will fold geometrically. And then the valid layer order tells us for every pair of overlapping faces, two faces that share a point in their interior, which one is above the other, right? And that you can, that characterization on the faces then allows you to have a general directed graph to represent the layer ordering of these faces. which may not admit a linearization, but will still uniquely determine the folded state. And so we need some kind of representation like this so that we can communicate to others what these folded states are. And for having a foldable software, the minimum we need is to be able to represent these things and then have transitions from one folded state to another folded state, which would then be able to simulate origami. Now, this is actually a very difficult problem. It's known to be NP hard to even determine whether a crease pattern admits a flat folded state. And in general, there may admit an exponential number of folded states. So this can be a problem that's impossible to solve efficiently, but for many crease patterns, it seems that we can. It's not exactly clear what the qualities of the crease pattern have to be to make that efficient. But this talk is going to focus on one particular goal, which would be eventually to have software that simulates flat foldable origami, allowing common flat operations like simple folds, reverse folds, sinks, being able to reorganize the layers of the paper and maintain validity of folded states as you make these operations. But in order to do those things, I'm not showing you that. That's a dream. That's something we'll maybe do for future work. But the minimum we need is a verifier. We need to be able to verify if you give me a folded state, whether it intersects the layers or not, right? Whether it's a valid folded state. And generally, when we're making software like this, it's very useful to have example folded states so that you can test your algorithms. So there are many existing software that will take crease patterns and generate folded states, namely Ripa was, I think, the first one, programmed by Mitani-san here, who we heard from earlier today. And Meguro-san also developed some software which has been ported and improved and changed by various communities online. But those software are primarily crease pattern editors first, right? They're built for generating precise descriptions of crease patterns, but they also have as a feature a way to usually compute folded states and render their states. More importantly, being able to show you a rendering of those states. But they're built around usually finding one folded state efficiently. But of course, if you have an exponential number of folded states, that may take exponential time to be able to generate. Okay, so here are some examples of crease patterns with multiple folded states. This is one of probably the simplest example that you could have. You fold over two corners. This admits two folded states. That's two. Of course, many folded models admit only one, a unique folded state. Here is one that shows an example that shows that there could be an exponential number of folded states. So here we have, I don't know, F fingers on the right and F fingers below. And each of these blue lines here correspond to valley folds, which we can then fold across. And when we fold them across, we actually have an independent choice at each of the intersections here, which of the horizontal or the vertical flaps will be on top. And so the number of possible folded states here is 2 to the F squared, the number of folded states that are accessible here. So, but in a sense, such a crease pattern and its folded states should be able to be computable, or some representation of it should be computable more efficiently, because each one of these choices are actually not related to the other choices. They're decomposable. And that's really the main drive for being able to identify such situations and then take advantage of that when solving, generating folded states. That's the main contribution of the new algorithm that I'm proposing. So here's another example of a real world diagram state from a model. I was working on this winter for a Christmas tree. And it admits, for example, 16 million folded states, and putting this crease pattern into a Ripa or Orihime, well, for a Ripa, it crashes the program, and for Orihime, it takes forever. It will take a very long time to get there. Whereas with the software I'm going to show you today, it spits out all 16 million solutions in less than a second. So, okay, so first thing to talk about are how we represent these folded states. Orihime doesn't actually, it will render folded states that it creates internal representations of, but it actually doesn't export any states for use in other programs and things like that. ORIPA actually does provide a way of exporting that information in a novel format called OrMat, which essentially provides the vertex locations in the unfolded and folded states, description of the different faces listed by their vertex indices, one index, in fact. And then this matrix down here provides a layer ordering between every pair of faces. 0 represents that they are not overlapping, whereas 1 means that the one, I forget which is which, but 1 or 2 means that whether the row face or the column face is on top, okay? So one thing you'll notice here in this OrMat format is that these auxiliary lines, the crease lines, lines that might not be folded in the final model, aren't retained when they make the folded state. And so, so we actually see that these two triangles are actually represented as a quadrilateral in this OrMat format when it's being folded. And so we lose this crease information when we're computing folded states. So one of the things that my software would like to do is to retain that information if we're going to try to make diagrams where we want to retain that crease information. Okay, here is another possible output format, which is a standard called Fold that was developed by myself with Eric Demain and Robert Lang, which is instead of this kind of OBJ type format for parsing and this kind of novel matrix, it uses a standard JSON format that many languages have importers for, and it has basically the exact same information as the OrMat format, but in a more standardized importable format. So it has the coordinates that we're going to fold, the faces and their vertex arrays, and for every pair of overlapping faces, we have an order between them. And that layer ordering definition is a little strange in how they do it, but this layer order information is complicated like this because fold format is meant to be able to represent not just 2D flat foldable structures, but also 3D ones as well. And so there's no common notion of up when we have 3D folds. So the way in which we describe these layer orders is if I have two face indices F and G, whichever one, the direction of the face normal of face G, we say that F is above G if S is 1, and we say that F is below G if S is -1. Okay, so that's just a representation. And so the goal of flat folder is that we're not going to focus on crease pattern editing. We have good tools for editing crease patterns. What we want to be able to do is take in a crease pattern as input and then generate all the folded states of it or some subset therein, be able to retain auxiliary crease information in the folded states, be able to verify folded states on input, and try to improve the algorithm. And this was implemented in JavaScript in the browser, making it very easy to access this software. So what is the existing algorithm that we're wanting to improve? Well, it's the Ripa algorithm that Mitani-san has described in multiple places, but I'm just going to give a quick overview of that algorithm. So the first thing to do in the algorithm is to take a look at your crease pattern and walk that crease pattern in some spanning tree. And you fix some face, and then while you walk on this this thing, you overlap, you reflect each consecutive face and figure out where all those vertex positions should be. And actually, this can be done very efficiently. This is really fast to do. You can do this in n log n time because you have to sort lines around vertices to know which one's next. Okay, so this is a pretty easy algorithm to implement. That's the first step of the algorithm, and that's the same between Mitanya's algorithm and mine. The next step of the algorithm is to compute what I like to call the overlap graph, but I think is called the X-ray view in ORIPA. Basically, you take all the lines that are in the folded state, and they create a planar graph of different regions that have the same set of faces that overlap that region. And we associate with each of those cells, well, I call them cells of the overlap graph, with the stack of faces that overlap that cell, right? And so this graph actually can have complexity that's quite difficult. It can actually be take up at least cubic space, actually. So here's an example of a crease pattern where it requires cubic space to store. You have actually a quadratic number of cells in the overlap graph, and each one of those cells could have a linear number of faces in them. Okay, and then the last part of the algorithm is to try all possible stacking orders within each cell. And this is the exponential part where we have, n factorial different ways of ordering each set of faces in the cells. And then to check the constraints between them, you have to spend some more time to make sure that that thing works. So that can be at least exponential time. So the thing that we want to do in the flat folder algorithm is try to reduce as much work as we can in the exponential search to try to limit that search as much as possible. So this part of the flat folder algorithm is exactly the same. We get those vertex positions, but we forego calculating the overlap graph instead by trying to compute the overlap orders on the pairs of faces directly. So first we construct the variables for each pair of faces. We construct their intersection or see whether they intersect. It's a binary. And this can clearly be done in cube time for every pair of faces. We can compute their intersection, but actually we can take advantage of the fact that the crease pattern is a planar graph. And for planar graphs, the average degree is constant, at most average 6. And so when you sum this up, actually computing these all can take quadratic time instead of cubic time. And then once we have all of those variables, the things that we know need to be assigned a layer order, then we construct the list of constraints that need to be satisfied. And there's 4 different types of constraints that need to be satisfied. The first set I like to call tortilla. It's basically we have 2 flat planes and we don't want them to intersect each other, right? And so we can compute all of these such constraints that need to be satisfied in quadratic time by comparing every pair of intersecting edges or an edge with a face. And each of these constrains 2 variables. So these 2 faces overlap and these 2 overlap, and they need to have the same assignment, basically. And the same goes for the other types of constraints too. This one I like to call taco tortilla. It has a bunch of different states that it could be. Some of them are valid, some of them are not, but I can enumerate all of them. There's just a constant number of them. For taco, we have this, again, quadratic numbers of constraints. We can compute those. This is the more complicated in terms of the number of variables that they constrain. There's 6 variables that are constrained here. But then there's what I like to call a transitivity constraint. This is one that the overlap, Ripa algorithm actually gets this for free, right? Because of course, everything in a stack in the overlap graph, a cell of the overlap graph, transitivity, as long as you have an ordering of them, holds because all of them overlap. But if we're not going in this route, then for every 3 faces that have a mutual point in their interior, we need to have transitivity. So if A is over B and B is over C, then A is also over C. That doesn't generally hold unless there is a point in their interior, and we can construct this in cubic time, okay? So we have a bunch of variables that we compute and a bunch of constraints, and we check the folded state. This gives an n-cubed algorithm where we can directly compute whether a folded state is correct by just computing all of the constraints and verifying whether the assignments of those variables is correct. So that gives a clear n-cubed algorithm. So here's an example of the variables and constraints associated with the preliminary folder, the square base, very common origami object. Here we have the variables on the left here, which are pairs of faces that overlap in the folded model. And over here on the right, we have different constraints. And I'm going to make a constraint graph that connects each of these constraints to the variables that it's associated with, right? And the degree of the constraints is constant. So this whole graph has n at most cubic size. It's a bipartite graph, constraints on the right, variables on the left. And the first part of the algorithm, if you have an assigned crease pattern, one assigned mountain folds or valley folds, then those variables, we actually, any 2 faces bounded by a crease, we actually know what their ordering assignment is based on whether they're mountain or valley. And so these black dots are already known from the assignment. So it remains to actually fill in what the rest of these are. And actually, each one of these, it happens to be the case that these constraints, if you fill in some of the information, other information can be automatically inferred. And so without doing any exponential search, actually, for this particular crease pattern, we can actually just fill in all the rest of it that are inferred from these constraints. And that can be done in n-cubed time, in cubic time, because it's a linear walk on the constraint graph. So that's the initial assignment. And then, of course, you have to do a brute force search. If you haven't been able to assign all the other things, some variables may be unassigned, and so you have to guess the remaining via brute force search. However, once we've assigned those initial assignments, the remaining variables may be in disconnected components in that graph. So here's an example of the variables that are needing to be assigned here. Each line here corresponds to a variable, an overlap between 2 faces. The overlap order between each of these fingers and the base here is automatically known from the assignment of these creases here. Those are shown in light green here, but all of the other pairs are actually in independent components. If I take a look at the constraint graph here, we have a bunch of transitivity constraints up here, and these are all of the variables. These are the variables that are assignable from the initial assignment, but all of these other ones are not related to the others, right? So we can actually determine that in linear time in the size of the constraint graph and assign these independently, right? So by that initial assignment, we actually decompose the constraint graph into smaller subsets, potentially, that are much easier to brute force search on. So you have this initial work of n-cubed, but if you can break it up into these smaller components for SI from 1 to K, for example, you pay this exponential overhead by trying all the possibilities by doing the exponential search. But because these SIs are much smaller, we can do it much faster. And actually, so we solve those individual states separately, and then we combine them by taking their Cartesian product. Okay, so it's been implemented. It's freely available on GitHub. That GitHub also has a fold format library for a bunch of crease patterns that you can put in there and generate lots of folded states. And we post a folded state from various origami artists on an Instagram account every day. So that's basically the talk. There's future work on trying to use this to generate folded states of kind of diagram transitions from one folded state to another. But that's, I'm way out of time. So we'll end here and have just a couple minutes for questions.
Thank you very much.